Again to chemistry. We're looking today at nuclear energy. Nuclear energy is found by using Einstein's equation, E equals mc squared, where E is energy in joules, m is mass in kilograms, and c is the speed of light. There's some different values. I'm just going to keep it simple for you. 3 times 10 to the 8th meters per second. All right, so when we do these, we probably look at the following. How much energy is lost in the reaction of cobalt-6027 going to an abated emission plus nickel 60 over 28 if there is 1 mole product and the reactants, and cobalt is equal to 59.93382 AMUs and nickel is 59.9308 AMUs. And in order to do these, we do need to have these values, so make sure these down. These should be on your card probably. The mass of a proton, mass of a neutron, and mass of an electron. That's in the back of your book, so we can have them down. So let's start with the process. We take the mass of my products, which is nickel, plus the electron, and we get 59.93143 with proper sig figs. We subtract the mass of the reactant, which is the cobalt, 59.93382. When we subtract those, we get a negative 0.00239 U's. That's the mass lost. And because this is equal to 1 mole, we can say the mass is 0.00239 grams. We don't need to worry about negative, it's just that's the mass that's lost. So we're going to put that using the equation, E equals mc squared, put our value over 1, convert it to kilograms because mass has been kilograms, multiply by the speed of light squared. When we do, we get a value of 2.15 times 10 to the 11th joules. And technically that's over per mole since it is in 1 mole's reaction. So, and that's my answer. So let's look at a problem. We'll do this one in class. Calculate mass loss of 1 mole of substance in the reaction of carbon 11 to boron 11 plus abated emission if the reaction releases 2.87 times 10 to the 11th joules. Now, there is another type of problem we can also do. It's called the energy from the binding energy. Binding energy is the energy that holds the nucleus together. That's that gamma energy that we react, all right? And it's the mass of the atom as compared to the mass of all the protons and neutrons in the nucleus, and we refer to that as mass defect, the difference between what it should be and what it actually is. So let's look at a problem. Step 1, find the mass defect from the binding energy of helium per nucleon and per mole. So we look at our protons, neutrons, and electrons again, and we have helium, which is 4 over 2. There's 2 protons and 2 neutrons, so we multiply 2 times 1.007276467 because that's the mass of a proton, and 2 times 1.008664916 U's, that's the mass of a neutron. We get those values and we add them together, and we get 4.0318882766 U's. But if we look at a periodic chart, we see the mass of a nucleon of helium is 4.002602 U's. So the difference there is 0.029281 U's. That's my mass defect, okay? Take that value, and I want to convert it to grams. I use Avogadro's number, 6.02 times 10 to the 23rd U is 1 gram. We want to convert it to kilograms, and we then multiply by the speed of light, so it's mc squared. We get 4.3776 times 10 to the minus 12th joules per nucleon. And we want to find out what it's going to be in per mole, and we use Avogadro's number to do that. 6.02 times 10 to the 23rd nucleons is 1 mole. So we get 2.6353 times 10 to the 12th joules per mole. Those are my answers. All right, we'll do this one in class. Find the mass defect from the binding energy of nitrogen per nucleon and per mole. That's it. Take care. Be good. Bye.